Now we have at each pixel a feature vector, and we simply want to classify the feature vector as being a face or not a face. And we argued that a very efficient way of doing this would be by using decision boundaries. And that's exactly what support vector machines do. They compute for you the best decision boundaries to use. Support vector machines, by the way, are widely used not just in computer vision, but in many different fields. First, let's talk about decision boundaries. So, in particular, we're going to focus on linear decision boundaries. Let's assume for a minute that our feature vector is of dimensionality 2. You have f1 and f2. These points are, for instance, your faces, and these are your non-faces. The decision boundary, in this case, this is a two-dimensional space, is a 1D line. If it's a linear decision boundary, it's a 1D line, which divides up the space so that when you have a new feature that comes in, if it happens to lie on the left side of this line, we call it a face, and if it happens to lie on the right side, we say it's a non-face. So, this decision boundary can be written using the equation of the line, w1f1 plus w2f2 plus b equal to 0. In vector form, it can be written as follows. So this is w is your coefficient vector, and f is your feature vector, and b is a scalar which corresponds to the intercept. So you have w transpose f plus b equal to 0. And now let's say that you have a new feature that comes in. You simply plug that feature f into the left-hand side right here. And if that happens to be greater than 0, then perhaps it lies on the left side here, and we say it's a face. If it happens to be less than 0, then it lies on the right side here, and we say it's not a face. Very simple. And now, of course, if you have a feature space which has a higher dimensionality, the same approach applies. So if you're in three-dimensional space, feature space, then the linear decision boundary would be a 2D plane. So you see this plane that is going between the two clusters in this three-dimensional space. And once again, you can write the equation of the plane using the same form, w transpose f plus b equal to 0. W and b describe the plane, f is the feature. And once again, you can plug an f in here, and if the left-hand side is greater than 0, then you're on this side of the plane. If it's less than 0, you're on this side of the plane, and that's all you need to do to figure out whether it's a face or not a face. And linear decision boundaries of the same form can be used irrespective of the dimensionality of the feature space. If you happen to be in an n-dimensional feature space, then you have an n-1 dimensional hyperplane. That's your linear decision boundary. You can't show n-dimensional spaces here, but that's again a plane. It's a hyperplane because it's in high dimensions. So this is your equation of the plane in high dimensions. And again, you have the same form, w transpose f plus b equal to 0. And the same test applies in order to classify a feature as a face or not a face. So the question really is, what is the optimal decision boundary to use given these faces and given these non-faces right here? We know it's going to be, we're looking for a linear decision boundary, but which one is it? In other words, what are the parameters w and b? Well, you can see that instead of this line right here, if I use this line, I still have a decision boundary that seems to work very well, or I could use this line. In all of these cases, these points that I've shown here, which is a training data, will be categorized, classified just fine, but we know that given a new point, it could actually end up having different results based on which of these decision boundaries you use. So that brings us to ask the question, what is the best decision boundary to use? How do you evaluate the quality of a decision boundary? We do this by defining what's called a safe zone or a margin. That is, it is the width that you can extend this boundary or thicken this boundary by so until you hit features on both sides. So you see that we've extended the safe zone right here, which is the shaded orange region. We've extended it until the point that it ends up hitting these 2 points on this side and these 3 points on this side. So the width that the boundary can be increased by before it hits a feature point on at least one feature point on each of the 2 sides, that is the safe zone corresponding to any chosen decision boundary. And the thickness of this band that you're looking at here is called the margin. So you can see that different decision boundaries, different lines here will produce different safe zone. So here you have this decision boundary, this is the margin. In this case, you have a thinner margin for this decision boundary right here. And once again, the problem is that if you have a new feature that comes in this case, it is considered to be a face. In this case, it's not a face. So we want to choose the decision boundary which maximizes the margin. That's what the support vector machine does. So if you look at what the support vector machine does, it basically is trying to find a decision boundary which has a safe zone, which has a maximum margin right here. And why is it called a support vector machine? It's because when you go to this maximum margin, you basically are touching these points on either side, face points and non-face points in our case, and these points can be seen as supporting the safe zone, and therefore we call them support vectors. What's interesting about the support vectors is that once you've computed the support vectors, you know which points actually lie on the boundary of the safe zone. You can essentially ignore all the other features. That's all you need to represent your decision boundary. And you don't need these other points on either side. So now let's take a look at how we compute the support vector machine. So what's given to us is k training images, I1 through Ik, right here, and their corresponding hard features, F1 through Fk. And along with that, we are also given these labels, lambda 1 through lambda k, where lambda is equal to 1 if the image is a face and lambda equal to -1 if the image is not a face. So that's your training data right here, shown down here. And what we want to find is the decision boundary W transpose F plus B equal to 0, which gives you a maximum margin with a safe zone that has a maximum row, thickness row right here. Okay, so let's see how we formulate this problem. For each training sample, that is feature Fi and corresponding label lambda I, if lambda I is +1, we know that W transpose Fi plus B is greater or equal to rho divided by 2. That is, it must lie beyond this line right here. So this is the decision boundary you're looking for. This distance here is rho divided by 2, and we know that if it is a face, it must lie beyond, further away from this decision boundary, at a distance greater than rho divided by 2. That's what this constraint is. On the other hand, if lambda is -1, then W transpose Fi plus B is less or equal to minus rho divided by 2. That means it must lie on this side of the safe zone. So what's nice here is that you can combine both these into one expression, which is lambda I times W transpose Fi plus B must be greater or equal to rho divided by 2. So you get one expression right here. Okay? And now, if you happen to be a support vector, remember what a support vector is. It's a vector that is actually touching the safe zone. It lies on the boundary of the safe zone. So if you happen to be a support vector, well, let's say S is the set of support vectors we're trying to find, and you happen to be a support vector, then we know that lambda S, that's for the support vector, it could be a face or not a face, times W transpose Fs, that's the feature vector for that support vector, plus B must be exactly equal to rho divided by 2. In other words, support vectors must be exactly a distance of rho divided by 2 from the decision boundary. Okay, so then we can find the W, B, and the support vectors that maximize rho using this constraint right here. And there are functions that allow you to do this. For example, in MATLAB, you have SVM train, and you get the support vectors. You get the support vectors, you get the coefficients W and B of the decision boundary, and you also get rho, and it happens to be the maximum rho you can get. So now we can classify new features based on the support vector machine that we just computed. So you have har features F for an image window, and you have the SVM parameters, and you first compute the distance D equal to W transpose F plus B. And if D is greater or equal to rho divided by 2, we know it's a phase. It lies on that side. If D is less or equal to minus rho divided by 2, it's not a phase. If D lies between 0 and rho divided by 2, it's probably a phase. So it's inside the safe zone, but it's on that side of the decision boundary. If it's between 0 and minus rho divided by 2, it's probably not a phase. Okay, so now let's take a look at an example. This is phase detection applied to a clip from the movie Matrix. This is thanks to Michal Hruby. And here you see that phases have been detected. Each one of these windows is a phase, detected phase. You get multiple windows around the same phase because the detector is telling you that there's a bunch of pixels that are close to each other that produce features that all were classified as phase features. And so one can imagine using something like non-maximal suppression, which we discussed earlier in the lecture on corner detection, to then take this cluster of windows and come up with a single window. But let's not worry about that here. I'm going to play the video and you'll see how frontal faces, it's mainly for frontal faces, are detected pretty well. Get the idea. So now, let's close with a few remarks related to phase detection. First, current phase detection systems are pretty mature. They're not perfect, but they're pretty mature, and we know this because they're being widely used today. Second, when it comes to phases that are non-frontal, which means that you could have a profile, say for instance in the extreme case, then in those cases, it's often is beneficial to train additional detectors and classifiers to go with them. Because if you actually include faces with the entire range of poses that you're interested in, you might sort of dilute the effectiveness of the detector. So you may want to break it down into multiple detectors that function on frontal faces, maybe things that are more in the 30 to 60 range, and then profiles. And we know that it is a very successful vision technology, widely in use today in cameras, for surveillance, security, biometrics, and so on. And finally, the performance continues to improve. In fact, if you add on top of this face recognition, which is figuring out the identity of the person inside the window, then it turns out that machines are now, especially with deep learning, beginning to surpass the performance of the human visual system.